Today we are going to learn about the empirical rule and z-score percentages. By the end of this video, you should be able to use the empirical rule to estimate probabilities based on z-scores and use the standard normal probability table to determine probabilities and percentiles based on z-scores. First, let's talk about the normal distribution. So this picture is called a normal distribution. In the normal distribution, the mean and the median are the same number or very close to each other. As you can see, this picture is symmetric, and lots of things in nature are normally distributed or fairly close to normally distributed. So, when we are looking at a picture like this, whatever number is your mean will be in the middle. And then we are counting by standard deviations. So this next line would be the mean plus 1 standard deviation. The next one would be the mean plus 2 standard deviations, and the next one would be the mean plus 3 standard deviations. On the other side, we have the mean minus a standard deviation, the mean minus 2 standard deviations, and the mean minus 3 standard deviations. So if we are talking about z-scores, that would make the z-score for the mean 0, the z-score for this next line 1, then 2, then 3, and the z-scores on the other side, -1, -2, and -3. Now there are some interesting properties of the normal distribution called the empirical rule. The empirical rule says that 68% of the data in a normally distributed set of data fall within 1 standard deviation of the mean. So that means that 68% of the data would be in this region, between a z-score of -1 and 1. Since we know that the normal distribution is symmetric, we know that we can cut this in half. So 34% of the data are between a z-score of -1 and 0, and 34% of the data are between a z-score of 0 and 1. The next part of the empirical rule says that 95% of the data falls within 2 standard deviations of the mean, meaning that 95% of data is in this region and has a z-score between -2 and +2. And if you do the math, subtract out the 68% that's in the middle and then divide by 2, that means that each of these sections between -2 and -1 and between +1 and +2 account for 13.5% of the data. The last section of the empirical rule says that 99.7% of data falls within 3 standard deviations of the mean. So that means that almost all of the data has a z-score between -3 and +3. And again, if we do the math, subtract out the 95% that we've already accounted for and divide by 2, each of these little sections is 2.35% of the total data. That means that on each end, 0.15% of data has a z-score of less than -3 or greater than +3. So those are very rare values. Now we are going to use the empirical rule to estimate some percentages. The lifespan of turtles in a particular zoo are normally distributed. The average turtle lives 91 years with a standard deviation of 21.4 years. Shade the regions under the curve for turtles living longer than 48.2 years. So, we know the mean, we know the standard deviation. Let's label our normal curve. We know that the mean goes in the middle, and we know that we are adding or subtracting the standard deviation for each one of these lines. So here we would add the standard deviation, then add the standard deviation again, then add the standard deviation again. On the other side, we would subtract the standard deviation and subtract the standard deviation again and subtract the standard deviation again. So we want to know which sections of this curve account for the turtles living longer than 48.2 years. 48.2 is here. So that means this region is all of the turtles that live longer than 48.2 years. In part B, we want to figure out what percentage of turtles this is. So if we use our empirical rule, we can figure that out. So the mean is in the middle. We know that everything to the right of the mean is 50%. And then by looking back here at this diagram of the empirical rule, we know that this section is 34% and this section is 13.5%. If we add all of those percentages together, we get that this would be about 97.5% of turtles would live at least 48.2 years. Next, it asks, if there are 200 turtles in this zoo, how many will live for longer than 48.2 years? So to figure that out, we're going to use the percentage we found in part B. We're going to change that percentage to a decimal and multiply by the total number of turtles. And that gives us that approximately 195 of the 200 turtles should live for longer than 48.2 years. But there is a downside to the empirical rule. Let's suppose we look at the scores for one component of the SAT. Assume the results are normally distributed and 45,000 students took the exam with a mean of 528 and a standard deviation of 87. Let's label our normal curve. The mean goes in the middle, and then we add the standard deviation. And then we subtract the standard deviation. How can we determine what percentile a student who scored a 680 ranked? Well, 680 would be about here. That's in the middle of one of our sections for the empirical rule. So when that happens, we need to use a different method to figure out the percentages. First, with this problem, we need to define what a percentile is. If you've taken the PSAT or other standardized tests, you might have noticed on your score report that it gives you a percentile rank. And that tells you what percent of the data is below a given score. So if on your standardized test results, it tells you that you are at the 50th percentile, then that means you scored better than about half of the people who took that test. Since 680 is not one of these numbers that we marked on our normal distribution, we need to find the z-score. And when we find the z-score, 680 is going to be our x. So z-score is going to be 680 minus the mean, which is 528, divided by the standard deviation, which is 87. And if you type this in your calculator, you get that the z-score is 1.75. Then you're going to go to the z-score table. This table tells you what percentage of the data is below a given z-score. One side of the table has negative values, the other side has positive values, and that refers to the z-score. So since our z-score is 1.75, we're going to go to the positive side and go to the row that says 1.7, which is here, and then we're going to go over to the column for 0.05. So that means we are looking up the z-score that is 1.75. So the table gives us the number 0.9599. So let's write that down. So our table value is 0.9599. So if we change this to a percentage, that means that 95.99% of people scored below a 680 on this section of the SAT. We were asked to write a percentile, which is always given as a whole percentage. So if we round this, this would be the 96th percentile. So this person scored better than approximately 96% of people who took this exam. The next question asks, what percent of students scored between a 480 and a 680? Well, 480 would be about here. So we need to find the z-score for 480. So if we have 480 minus the mean, which is 528, divided by the standard deviation, which is 87, we get that the z-score is negative 0.55. Then we want to look this up in the table. So since we have a negative z-score, we need to go to the negative side. We want to go to negative 0.5 and then go over to the column that says 0.05. So our table value is 0.2912. When we want to find the percentage between two values, you want to take the numbers from the table and subtract them. So we already found the table number for 680. That was 0.9599, and we want to subtract the number that we got when we looked up the z-score for 480, which was 0.2912. So if we subtract those, we get 0.6687. So that means that 66.87% of people scored between a 480 and a 680. If we want to know how many students scored better than a 480, we would need to find the z-score, but we already found that. And we already looked up that value in the table. So I'm going to draw a small sketch of the normal curve. 480 was about here. If we want to know how many students scored better than a 480, that is to the right side of 480 on the normal curve. The table gives us the probability that somebody scored less than that value. So to find how many students scored better than a 480, we want to do 1 minus that number from the table. And that gives us 0.7088. But since we want to know how many students, not the percentage of students, we need to take this number and multiply by the 45,000 students who took the test. And that gives us 31,896 students. So that many students scored above a 480 on this section of the SAT. The next question asks, what score is in the 68th percentile? So for this problem, we're going to work backwards. If we knew that something was at the 68th percentile, that would mean that the table gave us a value of 0.6800. So let's go to the table and see approximately what z-score that would be. If we look through all of these numbers in the middle of the table to find the one that is closest to 0.6800, we find this number here that is 0.6808. And that number corresponds to the z-score of 0.47. So that's what we're going to use. And since we are trying to find the score, we are trying to find x. So now let's just use the z-score formula. We have 0.47 equals x minus the mean, which is 528, divided by the standard deviation, which is 87. And then we just solve that for x. So if you multiply both sides by 87, you get 40.89 equals x minus 528. And then you add 528 to both sides, you get x equals 568.89. So their score was approximately 569. Let's look at two more examples. The useful life of a radial tire is normally distributed with a mean of 30,000 miles and a standard deviation of 5,000 miles. The company makes 10,000 tires a month. What is the probability that if a radial tire is purchased at random, it will last between 20,000 and 35,000 miles? So I'm going to draw a quick sketch. If I know that the mean is 30,000 and I want to find what the probability is getting between 20 and 35,000, that means I'm looking for this percentage. So I need to find the z-score for both 20 and 35 and then look them up in the table and subtract them. So if I find the z-score for 20,000 miles, that will give me a z-score of -2. If I find the z-score for 35,000 miles, that will give me a z-score of 1. Now, because it does not tell me to estimate using the empirical rule, I'm going to look these up in the table. So if I go to negative 2.00, I get that table value, 0.0228. And if I look up 1.00, I get that table value, which is 0.8413. So negative 2 gave me a table value of 0.0228, and 1 gives me a table value of 0.8413. So to find the probability that something is between these two values, I want to subtract them. And that gives me 0.8185. Since the problem asks for the probability, I'm going to leave my answer as a decimal. If it asked for a percentage, I would change it to a percent. Lastly, we have that the weights of eggs produced on a farm are normally distributed, with a mean of 1.4 ounces and a standard deviation of 0.4 ounces. To be graded extra large, an egg must weigh at least 2 ounces. What is the probability that an egg from this farm would be graded extra large? So let's sketch a normal curve. My mean is 1.4. I want to know what the probability of being greater than 2 is. So I'm looking for that probability. I'm going to start by finding the z-score for an egg that weighs 2 ounces. So if I have z equals 2 minus the mean, which is 1.4, divided by the standard deviation, which is 0.4, that gives me a z-score of 1.5. Then I need to look that up in the table. So if you go to the positive side, go to 1.50, that gives you a value of 0.9332. Since the table tells me the probability that something will be less than that z-score, and I want to know the probability that something is more than that z-score, I need to do 1 minus that number that I found in the table, which gives me 0.0668 as my final answer. So the probability of an egg from this farm being extra large is 0.0668.